Welcome everyone. My name is Keith Gregory, and this is the Philadelphia AWS meetup. If you were planning to be on a flight for Dallas, time to check your boarding pass. So, there's been a few changes with the AWS meetup. In the last month, Steve and Jeremy and Dave, who were the former organizers, have passed the baton to myself and Grant and Chariot Solutions, who are the current organizers. As you can tell, things are a little bit not so smooth at the beginning, but we're hoping that it will work out. One thing I want to call out is that as a meetup, we need participation. So if you have something you want to talk about, an AWS journey of any sort, just let us know. We'll figure out the schedule. If you have a venue, that would be great. We can keep hosting at Chariot, and Health Verity in Center City has offered to keep hosting. So we have good venues, but we could always use more. Love to have one out around the Radnor or Malvern area. And speaking of Health Verity, they're going to be hosting next month. And Logan, who is, I believe, their head of IT, is going to be talking about the Amazon CDK, or Cloud Development Kit. So infrastructure as code to write infrastructure as code. And in April, we have a speaker from AWS who will be talking about Bedrock and Amazon Q. We do not currently have a venue, but we'll end up here if we don't find one. I am going to quickly share a couple of other upcoming conferences. And of course, with Zoom, I have to go through a multi-step process to share windows. Upcoming conference, yes. You as slideshow? Excellent. Okay. So in June, if you haven't heard, AWS Reinforce, which is Amazon's security conference, is going to be happening in Philadelphia. And I'll leave this up if you want to snap a picture of these, but I'll also put links onto the Slack. And which reminds me, we do have a Slack for the user group. If you give your email to Grant, he will get you an invite. Oops, sorry.
Was that free?
Reinforce is probably not free.
Oh. I've heard of reinvent, I know that's not free.
Yeah, Reinforce is a little bit weird. They still have not put an agenda up or the keynotes or even a registration page.
This is the first time this event's happening?
No.
Reinforce? Okay.
Reinforce has happened for several years.
The videos are available afterwards at some point?
Yes.
Okay.
Yeah. Second one is B-Sides Harrisburg, and either Bert from AWS or Steve from Alpine Cyber passed this to me. I'm not too familiar with this group. It's a cybersecurity group in Harrisburg. They are having a one-day conference on Friday, April 12th, which anybody know what April 12th was, the anniversary of? Sinking of the Titanic.
Oh, yeah.
And if you'd like to speak there, their call for papers is open until March 1st. And then lastly, some self-promotion. Chariot, in addition to being a consulting company, which Grant will tell you about, also organizes the Emerging Technologies East Conference, formerly known as Emerging Technologies for the Enterprise. And this is the 15th year we've been doing that. It's taking place at the Science Center over 2 days in Philadelphia, and we generally get a pretty good list of speakers. To give you an idea, our last in 2021, I think, was a virtual conference. We had Alan Kay speaking on one day and Cory Doctorow speaking on the next as keynotes. I'm not sure if he's the keynote, but I know that Dave Thomas, co-author of Pragmatic Programmers, is going to be speaking this year. So that is my plug for ETE as well as other conferences. I'm going to let Grant stand up and give the venue host.
Hi, everybody. I'm Grant Hartman. I'm the Director of Client Engagement here at Chariot. As Keith alluded to, for those of you that don't know us, we're a consulting company. We specialize in custom software development and data engineering. From an AWS perspective, we really specialize in deployments and building and optimizing data pipelines. And you'll get a flavor of that tonight with Keith's talk. But our clients typically bring us in to help them with some of their most complex challenges. been around for 20 years. Most of our teams located here in the Philly area. And, if you have challenges at your companies or know people that do, we'd love to talk to you. I will say Chariot produces a lot of thought leadership and content. Keith writes a regular blog, semi-regular, around AWS, cloud deployments, data engineering. A good way to get that content is to follow us on LinkedIn. Just search for Chariot Solutions, and you'll find us there.
All right. Well, I'm going to get started. So the title for tonight is Aggregating CloudTrail log files. But it's not just about CloudTrail. It's more about building a data pipeline and the thinking that goes into a data pipeline. And CloudTrail I picked because it happens to be a really good example of the problem that I'm trying to solve. And it's something that everybody has the ability to enable. So you may be in a similar situation. And the problem is small files in a data lake. And the reason it's a problem is if you use Athena or Redshift Spectrum or Glue or really anything else to read a data lake, small files will absolutely kill your query performance. And the reason that happens is it takes about 15 milliseconds to read a 1 kilobyte file from S3 onto EC2. I've done a series of benchmarks in this. It takes 20 milliseconds to read a megabyte. So only 5 milliseconds different for 1,000 times larger file. And if you think about what's happening behind the scenes, when you go out to make a request to S3, you actually hit basically a web server in the front end. And that web server checks your authorization, your secret key, and then it has to figure out where in the back end it can actually find that file. And that all takes a lot of time, or at least some significant fraction of 15 milliseconds. Once it's found the file, streaming it is a very high bandwidth, at least to EC2 or anything else on the AWS network. So 67 files per second per reader thread. Seems really fast, except if you have millions and millions of files, it's not very fast at all. And Athena can spread out and have lots and lots of reader threads, but it still takes a lot of time. And a few years ago, again using CloudTrail, I wrote a blog post to demonstrate just how big an effect this is. At the time, we had about 1.6 million files in our CloudTrail repository, and it took over 3 minutes to run a very simple query that just counted them all. Then I aggregated those files by date, coming out with just under 2 years at this point in time, and it took 6.3 seconds to run the same query. So this is really the difference between having lots of little files and having a small number of large files. The large files or large-ish files play to Athena's strengths. And by the way, I'm going to pause every so often for questions, but feel free to interrupt. And if people online, Grant's watching the chat window, so feel free to write your questions there. All right, so why CloudTrail? And first off, how many people are familiar with CloudTrail? Okay, for those who aren't, if you think of AWS as a web server, which it is because every AWS request is either a get, a put, or a post, then CloudTrail is the access log. So when you want to spin up an EC2 instance, you're basically making a put request, I think it is, to the EC2 endpoint with the parameters such as the subnet you're going to deploy to, the security, the key pair, so on and so forth. And that's handled basically as a web server backend, and AWS writes information about that request into CloudTrail. And it's really incredibly useful. If you don't turn it on, I highly recommend you do that. It lets you answer questions such as, who spun up that EC2 instance that's costing us $1,000 a month? And they didn't bother to put any tags letting us know who they were. Or who outside of our corporate network is attempting to decrypt secrets? Important stuff. And the way it works is about every 15 minutes per account, per region, it writes a file into S3. that contains JSON records describing all the events that happen in that 15 minutes. That's not too bad if you are like me and my personal one AWS account where I do almost everything in US East 1. You're looking at about 100 events a day or 100 files a day. Chariot, we have a bunch of sandbox accounts that our developers use to work things out. So we're figuring out how to use specific services. We have over 4,000 files on a typical day, or in the past 4 years, 4.6 million files. Now, again, you try and read this at 67 files per second, it's going to take a long time. And a real killer is most of the files are small. And if you think about it, yeah, during the day, people might be working and might be doing all sorts of things with AWS, but in the middle of the night, the only thing that's happening is that Trusted Advisor is going out across all of the regions that are enabled that we can't disable and making queries about what's going on in those regions and writing a few files. And in fact, of our 4.6 million files, 44% of them are less than 1 kilobyte long. So any query against CloudTrail is going to be reading all these tiny files. And CloudTrail, as I said earlier, is a great example because all of you have the ability to use it. But it's not the only case where you run into the same problem. You know, if you think about like web server clickstream data or mobile app clickstream data, right? You're recording what people are doing as they visit your web server. And let's narrow in and give a very specific example. You're an online grocery store. Now, people are going to be using your site a lot for very narrow times of the day. Not too many people are going to be ordering groceries at 3 a.m. A lot of people are going to be ordering groceries at maybe 8 a.m. before they go off to work. Now, let's say that you take this clickstream data and you're feeding it through something like segment.io, which pipes it into a Kinesis stream, and you use Kinesis Firehose to put these records onto your data lake. Well, you're going to be in the same situation as CloudTrail. 3 a.m., you're going to get files with probably nothing or very few events in them. But 9 a.m., 8 a.m., you're going to get pretty big files. So it's the same problem. And of course, I'm here talking to you, so I have a solution. And we're going to start with kind of a standard Lambda-based data pipeline, okay? And in this pipeline, we have CloudTrail over here on the left. It's feeding event files into a source bucket. Now, a traditional Lambda-based pipeline would invoke the Lambda when a file drops into the bucket. You know, if you have something like you've got a data feed that someone's uploading on a regular basis, trigger the Lambda when that happens, and write the results into the destination bucket. In this case, we don't want to do that. We're getting 4,000 files a day. We don't want to be running this Lambda for every single file. So a technique that I really like, and if you're not familiar with the AWS iconography, this is an SQS queue. And the idea is that you put a message onto an SQS queue, and that queue triggers Lambda with that message. And there are a couple of really nice features. It's very closely tied, SQS and Lambda. So SQS will invoke a Lambda with the message, and if the Lambda fails, it comes back and SQS is going to retry. And after some configurable number of tries, it drops into a dead letter queue. And that's fabulous because if something shows up in the dead letter queue, you, as a developer, know you've got a problem. And you can look at the message that caused that problem, and you can either send it back into the transformation to take a close look or try and process it on your desktop, do whatever. Let's assume you figure out the problem. You then pop it back into the queue. You redrive it in Amazon's term. I love that term. And it runs the transform again and hopefully works this time. So very, very nice. And that's what I just said. And here's a code sample. And for code samples here, they're partly because I'm going to upload a PDF so you get to see the code sample tomorrow if you're on the Slack or on the meetup. But I will quickly talk about it. So this is code to put basically a month's worth of messages onto SQS. And right there, client send message is the core of it. That's all you need to do to put a message onto an SQS queue, assuming you have the right permissions. Now, that kind of begs the question of, you probably want something else putting a message on the queue every night instead of you running this code every day or every week. So you can tie in EventBridge and the EventBridge scheduler to put messages on the queue. And some people would say, well, use EventBridge to invoke the Lambda directly, but then you don't get the benefits of the dead letter queue. So I should have put it in that diagram of EventBridge, 1 a.m. UTC puts a message on SQS, which triggers the Lambda to do the previous day's work. Any questions about that? Yes.
Is there any concern about, it looks like you're moving the event from the source to the destination? Like if something were to go wrong, or that transformed it in a way that you did not like, or it lost data, like, are you moving it, or does it still live in the source?
It still lives in the source, and I actually have a slide talking about that. But yes, the question is, are you moving or transforming and copying? And definitely transform and copy. Drew.
Is there a way, like I see CloudTrail to source, is source like the middleman? Can CloudTrail like invoke the Lambda itself instead of like pushing it to an S3 bucket and then the Lambda going?
No. CloudTrail can write to either S3 or to a CloudWatch log.
Okay.
Too many things that have cloud in their name. So one thing I wanted to show this loop for is I'm dumping a month's worth of data into the queue. And that brings out what I think is one of the nicest features of SQS, is it scales. SQS will invoke your Lambda concurrently, spin up multiple Lambdas until it cleans out its queue or until it hits a configured limit. And it really scales up pretty quickly. I've tried this. You read the documentation and it says it tries 5 to start with and then adds another 100 every minute or 300 every minute until it either hits your account maximum or hits a configured limit. I'm going to say always, always, always configure a limit, because there are very few database servers in a real world environment that can handle 1,000 concurrent connections, 1,000 concurrent active connections. What's actually really interesting is up until putting this talk together, I thought that S3 was essentially infinite. But I've since learned that S3 scales. And if you have, say, 100 concurrent Lambdas, because you're processing a lot of data, you get this message from S3, which is a slow down message. And eventually S3 does scale up to support the volume. But by that point, your Lambda, if you've followed what I'm about to say in a few slides, has had an exception and died. Fortunately, everything's in the redrive queue, so you can restart it. The other problem you get into with this is you have a limited number of concurrent executions in your account. 1,000. You can go into the quotas page and update that. I don't know how much you can get. I'm sure that large customers have many tens of thousands that they can run. But with a normal account, you spin up 100 Lambdas doing this one data pipeline that can happen, without very much urgency, and that prevents one of your Lambdas that has a time-sensitive payload from executing. You've got a problem. So always, scaling is great, always set an upper limit. Any questions here? All right, let's talk about getting your files. Now, CloudTrail has kind of a weird file format that it uses, and it's a partition format, but it's partitioned, I think, exactly wrong. So starts off, this is an S3 object, starts off literal text AWS logs, followed by, if you have an organization, the organization ID, followed by the account ID within the organization, some more literal text, region, and then the date as month, day, year, and then finally you have individual files. And with a month, day, year, you're probably getting around 100 files within this prefix. And what makes this a problem is you may say, okay, yeah, it's just, use some sort of globbing, right? AWS log /star/star/ CloudTrail /star/ my date. And that works fine if you're in a shell reading things off a file system, but S3 isn't a file system. And this trips up a lot of people. S3 is a key value store. So this whole thing here is a key, and there's a file that's an object. These aren't really directories. These are just components in the key that are separated by slashes. And when S3 came out in 2006, if you passed in a portion of a key, like just that AWS logs, it would just start there and 1,000 at a time give you a listing of all the files that started with that prefix, is what they called it. Not a directory, but a prefix. In, as far as I can tell, 2010, they realized this was a bad thing. So they started to add a new API call that can go in and you can give it a prefix and tell it, give me all the child prefixes. So you give it AWS logs, it gives you the organization ID, give it the combination, it gives you that plus all of the accounts under there. So kind of one of the things that you learn about with S3 the hard way. Here's some code that does it. And basically the approach that I've taken here is just recursively work my way through the possible keys at each point. So at the top level, I have my root prefix, which I put my organization in. That's in a Lambda. You'd configure this as an environment variable. Retrieving accounts is just calling this function down here with that prefix. And then for each account, you can get the regions by taking that prefix, adding in the account ID, CloudTrail gets you under there. Pretty straightforward. Any questions? Good. So we have prefixes. Now we want to list the files for the prefix. And it's the same call. You're just passing some different parameters in. And this is actually the correct form of the call. The version I showed earlier has a subtle bug that 99.999% of people will not run into, but it returns results 1,000 items at a time. And generally, unless you're a very large organization, you're not going to have 1,000 accounts, and there aren't 1,000 regions. So I kind of shortcutted that. But normally you have to loop over results and say, is it truncated? Yes, get me more. So here we are in the Lambda. We've got a list of prefixes. We now have a list of files for each prefix. Now we need to aggregate the contents of those files. CloudTrail log files, as I said earlier, it's some JSON records. So I believe if you're doing a data pipeline, aggregate in memory. And historically, this was a very practical thing. Historically, Lambda would give you 512 megabytes of disk space, temporary disk space, but up to 10 gigabytes of memory. So unless you absolutely positively knew that you weren't going to hit that 512 megabytes, it was just easier to aggregate in memory. Today, you can get up to 10 gigabytes of disk, but it's still a lot easier to aggregate in memory because Lambdas get reused. Their execution context gets reused. So unless you clean up the disk space you're using, writing extra code, it may be sitting around and you might be doing a gigabyte every time you invoke the Lambda, and oops, we've invoked it 11 times, we've now failed. So I still think do your aggregations in memory. Getting 10 gigabytes of memory for a Lambda is really cheap. And here's the code we do it. And this is all Python. This top function is a Python generator. How many people are familiar with Python, by the way? Oh, good. So you're familiar with generator functions. It takes a list of files, iterates through them, reads it, finds the top level records, and then basically yields each record found in the file. And then down below, we have an array, and we keep track of the size, and we simply iterate through all of the records returned by this, append it to the array. We have a desired size up here. If it's the array is larger than that size, we write a file and reset. At the very end, we write another file. So this is pretty much all of the Lambda, under 100 lines of code to do this aggregation. Oh, sorry, I left out the last bit, writing a file, another few lines of code. And I do want to comment here, again, I'm very wasteful with memory, right? I have an array of strings that's up to 64 megabytes in size. Now I'm taking that and I'm writing that into basically a string buffer. So making a copy of all that data. And then I retrieve the string buffer as UTF-8, which basically makes another copy of this data. And you may be cringing at this point, but this is really easy to follow, right? And again, memory is cheap. My time is far more expensive than any Lambda execution time, even if that Lambda is being executed tens of thousands of times. So this is kind of my approach to developing data pipelines. And now we're going to talk about making them resilient. We've made them simple. Let's make them resilient. Any questions about what I've gone through to date? Nope, good, nothing online. So I am not going to try a Yoda voice, but I think this is the #1 rule. No partial success. You either succeed or you fail, and you should fail loudly. Nobody's ever going to look at a log file to look for errors unless they have a reason to do that. So if you can't process something, don't try and catch it and write a log message. Just let your whole Lambda fail. Again, we've got the dead letter queue. That's going to capture the failures and make it obvious that someone should be going in and looking at log files. And then the second thing, which I think it was your question earlier, is item potency is your friend. And item potency, if you're not familiar with that word, it says that if you give something the same inputs, it will produce the same outputs. You can run something dozens of times. Files aren't changing on S3. It'll overwrite whatever you wrote onto the destination bucket. And this is part of, this is a copy. This is leaving the files on the source alone. And in the case of CloudTrail, I think a good practice if you set up CloudTrail is to turn on object lock. And the highest level, which I think is compliance lock, which you can't delete the files for a certain number of days without shutting down your account entirely.
Usually shutting down your account doesn't delete stuff.
Yeah. It's a little bit scary when you do that. And I worked with a client of ours to turn that on. I said, look, do 90 days. And if you're comfortable, up it to 180 days. It's useful to have the data that long. But yeah, it's scary to do that and realize that there's nothing you can do to stop this. So item potency, fail loudly. So how do you fail loudly? Well, AWS gives you some built-in CloudWatch metrics and alarms. This dead letter queue should never have anything in it, right? You can set an alarm that says, if you've ever got anything in the dead letter queue, send an email to the development team. Similarly, the trigger queue really on normal operations shouldn't have anything in it. If something remains in the trigger queue more than, let's say, an hour, that means your Lambda is not getting invoked. Again, set an alarm, send a message. And you can go through and create custom messages as well. So if we might not do this with CloudTrail, but for your clickstream data, you might know that you have a certain amount of data per day, normal usage. And hopefully it goes up and to the right, but you can set boundaries and say, okay, if I get more than this amount, something's gone wrong. Either our apps are sending too much or we're getting a denial of service attack or something. We should look at it. If we're getting below, that's also a problem. So, Drew.
Would the Lambda exiting not zero be something that you would want to alarm?
Nope, because, so the question for anyone online is the Lambda exits non-zero. Is that something you want to alarm? And not directly, because if the Lambda exits non-zero, the message is going to end up in the dead letter queue.
Okay, so it's redundant.
Yeah. And lastly, my controversial statement of the day, dashboards are all but useless. Nobody ever looks at them. It's not strictly true. If you work in a network operations center and have a big wall of screens, yeah, you'll probably see something that goes red. And a friend of mine repurposed a big screen TV in his office, which instead of running CNN, he put a Raspberry Pi hooked up to it to retrieve the system dashboard. So again, you can't help but notice that on the wall. But other than that, nobody keeps a dashboard open in their window. Sorry. Maybe someone here does. Don't take it the wrong way. And then the second thing, which I always throw in, I'm a logging zealot. And I'll give a little bit of history. I started working in this field 40 years ago now, just when interactive debuggers were starting to become useful. And I kind of developed the habit of always plugging my debugger into the code to test it. And that worked for about 20 years until I worked on my first web app, and the problem happens at 3 a.m. and what are you going to do? Well, for that, logging is your only way of figuring it out. And if you're not familiar with logging, you have logging frameworks that generally have different levels. Info level is kind of midway. I use that, just tell what's happening. So this is all the log messages out of a normal run of the Lambda. You know, what date you're looking at, how many files you found, how many records. Pretty straightforward stuff, and where it's writing to. Those are the things that anytime you look, you want to know that. The debug level is more detailed. It's actually looking at how many files it found. So this is that whole recursive go through the S3 keys to figure out how many files are in the list. It gives you that detail. So if you need that, if you're not getting data, you can start looking and say, okay, why aren't I getting anything for US West 2? Is it that it's finding 0 files with that prefix, which is okay, or is it just not checking? And the last little trick that I like that works really well with Lambda is I use an environment variable to set my log level. And by default, it's set to info. In fact, the code looks, and if it's not set, it's set to info. But when you need to debug, you basically have two choices. One is you go in, edit your actual source code, and rebuild, redeploy your Lambda with debug enabled, or you flip on, or you go into the console and flip the environment variable to debug and just let it run. So I found that working with Lambda to be a really useful trick. Any questions before we go on? All right, well, resiliency is useful, but not necessarily something that will get you really going. But like most developers, performance really gets me. And when I first ran this Lambda, I was shocked. It took 4 minutes almost to run. And I don't know about you, but that just seems like a long time, right? Especially since 4,000 files, okay, only under 19,000 records. It's taking 4 minutes to do this? Well, fortunately, my logging gave me some insight. And selecting that list of files, which is recursively transiting through the prefixes, took just under 13 seconds. Reading those files was the big number at 205 seconds. And I will say that we're going to see some numbers on different slides. I copied the numbers from different runs. There is variability between runs. Even the same source data produces the same output, but it might take a different amount of time. So, one comment, top level comment here is, where do you focus your effort? And I could probably get a second or two off of that, and that means absolutely nothing to the actual overall execution time. So we want to focus on reading the files. Okay, first trick for Lambda. If you have a performance problem, bump your memory up. And the reason is that for Lambda, unlike EC2 or ECS, where you can individually pick memory and number of virtual CPUs, memory determines virtual CPUs. And the ratio is that 1,769 megabytes, I don't know why it's not 2 gigs, but it's 1,769 equals 1 virtual CPU, which is in itself a very fuzzy metric. If you look at EC2, a virtual CPU is the speed of a hyperthread of a 2 gigahertz Xeon processor specific to the generation. Lambda, they don't even give that much detail. If you create a Python Lambda in the console, it gives you a default of 128 megs of memory, or a 14th of a virtual CPU. And this really slams people with cold starts. And not to be mean to Amazon, but I've found that Amazonians have been redefining the definition of cold start over the years. So my definition is very simple. A cold start is everything that happens for the first time. So give some background on Lambda. It's basically a container running your code. It starts up and runs your initialization code and then runs your actual handler for the first time. And things happen during that. With languages like Python or Java, which both do dynamic loading, Python, you import the Boto3 module, it imports a bunch of other modules, they all get compiled, turned into bytecode, and then they're ready to use. You create a Boto3 client, it does even more work, setting up a connection pool and a whole bunch of stuff. Cold starts, when you're first doing that, can be very painful. Generally, something that runs steady state, like this transformation, increasing memory isn't going to help. And as it turned out, it didn't. I bumped it up from 512 meg to a gig, no change. I bumped it up to 2 gig, and I think it actually took longer to run. Okay, how else can we look at this? So X-Ray is a service that Amazon provides for distributed tracing. And it's really nice, easy to turn on with Lambda, and it will, especially in a microservice environment where you have multiple things being called, you might have a web server here calling a whole bunch of Lambdas, it will show you the time taken by each of them. And it works with this idea of a segment of time, which by default for Lambda is the entire execution, but you can go down and drill down and define segments for individual functions. You can also patch the library to capture every call to AWS. So this seems like kind of a good idea here. Let's turn on X-Ray, let's patch the library, and unfortunately, we're making thousands of API calls. X-Ray is not designed for that. So it runs, it captures data, and it gives you a little bit of information, and this is useful information. It's figured out that the retrieved file list, in this case, takes 13.27 seconds, and you can see the various calls to S3, list objects v2, and this is actually initiating connection, and then this is all pretty consistent with my benchmarks, but ultimately, the overall execution time, it's pending. There's no end time showing here. And if you look up top here, Firefox is telling me you're slowing down this page because you're processing so much data. As it turned out, I went to the SDK to actually pull the trace data down, and it recorded about 600, 700 trace segments, calls to the S3 library. Then it just gave up. It had no way to record anymore. So X-Ray doesn't work. It's a great tool. I highly recommend trying it out. But if you're reading thousands of files, not going to do it for you. So next up, Python Profiler. And Python has built in a tracing profiler. So it records the starting and ending time of every method call in your program. And it will print out by different sorts, which we'll see in the next slide. And when you're not sure where you're spending time, this is a really useful tool. Unfortunately, the way most people use it, the cprofile.run, Lambda throws. They've done something to the Python library that makes that not work. Fortunately, you can create a profiler, enable it, call your function, disable it, and then print the stats, and it works fine. And you get something that looks like this, except with many thousands more lines in it. I've cut this out to show the interesting stuff. So total of about 3 million function calls for the overall program. At the top level, we have my aggregate and output function, which takes 252.764 seconds. It calls retrieve log records, which takes 248.831, which means it's about 4 seconds doing something else in there. That's going to drop down to the bottom. We don't really care about that. We care about the cumulative time. Reads files, 247. That calls the Bodo library to read the file, 246. And then you have a bunch of stuff in the Bodo 3 call chain. Bodo 3 is the Python SDK for AWS. And down at the bottom, you have the read method of the Python SSL socket module. And that's where we're spending most of our time. Now, if you look at it, each individual call isn't bad. We're 25 milliseconds, consistent with my benchmarks. But we're calling it an awful lot, and that adds up. So that's number one, telling me one of two things. Number one, it's saying, is there a problem with buffer size? We're reading 4,000 files, we have 8,000 calls. Is it a situation where we're having to make multiple reads out to S3 to make this work? And I don't know. That's an interesting question. I spent about 20 minutes trying to figure out if I could change the buffer size and finally gave up. And the other thing you might think of, well, is there any way that we can change the implementation so that we're not doing this? We're not paying this price. Of course there is. One of them's multi-threading. And this, on the surface, is like a perfect use for multi-threading. Multi-threading really pays off when you can overlap multiple IOs that are happening and just waiting, or when you have one thread that's using up CPU, such as parsing JSON files and gzipping or gunzipping, while something else is in IO. Lambda, we're using a fraction of a virtual CPU, so you really can't get a benefit with two things that are both using CPU time. But this is an example of code that does a lot of IO, should benefit. What gets in the way of that is the GIL, or Global Interpreter Lock. Show of hands, who's familiar with the GIL? Okay, so Python, up through version 3.12, it might be going away in 3.13, has an internal mutex that only allows one thread to execute Python bytecode at a time. And apparently that's because things happen with the memory management when you're running Python bytecode that you really don't want to try and coordinate. It is a tough problem. And that's all well and good. You know, this SSL read is not Python bytecode. It's a native function, so we should be able to overlap it. But if you remembered those numbers I called out, 252 seconds at the top level, 210 seconds, I don't remember them, for read, you've got about 30 seconds in there that's actual Python bytecode doing stuff. And that's not able to be threaded. So Amdahl's law, which I describe in a different way every single time. Tonight, it's the ability to speed up something through parallel execution is limited by what gets single threaded. So you have that 30 seconds. Yes, you can pass out those reads on multiple threads, but eventually you hit diminishing returns, and it happens really quickly. In my benchmarks, I found that you could get consistent, the 15 milliseconds, up to about 4 threads. Beyond that, you were just getting the times were going up. And then the last thing, the reason I really don't want to add multi-threading is the whole make this simple, make it easy. It's single-threaded, it's easy to figure out. Now, there's an interview question about threading, where the interview question goes something like, write a program that counts from 1 to 10, but have each counter or each print be in a separate thread. So you have one thread, you spin up these threads, and one of them says 1, and then another one says 2, and you have to keep it in order. And people occasionally get that and post it on Stack Overflow, and the Stack Overflovians pile on them saying, that's a stupid question. Nobody uses threads like that. Well, I've always thought it's a brilliant question, because it's really easy to spin up lots and lots of threads. It's really hard to coordinate the results from them. And for me, that would be a reason not to change this to make it a multi-threaded program, even if there wasn't a GIL. We don't need the complexity of doing a scatter gather of all these files and then processing the results. Okay, well, Keith doesn't like multi-threading, blah, blah, blah. How about different language? Python is slow, right? Python is horrendously slow. It's a scripting language. You read the file and you compile the file at the time you start running it. Maybe we do something like C or Go. But we're I/O bound, and a faster language is not going to help us with that. Now, with that said, there are some reasons that you might want to do it. Go has a really elegant multi-threading with Go routines and channels. And I almost wrote an example in Go, but decided not to. Java has decent multi-threading. It doesn't have a GIL to get in the way of multiple threads, although there are limits in the Java SDK of how many connections you can open. And you can use the queues in Java to coordinate between threads. It's a little bit more elegant, not as nice as Go. So this is kind of thinking about that, but really, okay, I'm a developer. I want to improve performance. I want to spend my days eking out that last little percentage. Is this really something I should be doing? And I remind myself of this every single day, and the answer is no. This Lambda runs at 1 a.m. normally. It takes 4 minutes. Nobody's standing up watching it. Every hour that you put into making it faster is an hour that you're not putting into something that adds value. And you might worry about price, but Lambda's cheap. 4 minutes, 512 megabytes of memory, that's 120 gigabyte seconds, which is the billing unit for Lambda, 0.2 of a cent. Or to put it in yearly terms, under $1. So definitely, this is not waste. This is not worth investing in improving, much as I hate to say that. And the other part is scaling it horizontally. So yes, there may be a reason, Chariot has 4 years worth of data. 4 minutes a day, that's going to take a long time. But if you scale it out, 8 executions a month is less than 15 minutes. That's a reasonable scale out, maybe 16. 100, by the way, will crush S3. Don't want to do that. You kick off that loop, put in the 4 years of dates on a Friday afternoon, and you're done. Come back Monday morning, and your data has been transformed. Probably do it overnight, in fact. All right, well, this is actually pretty good. When I've practiced this, this is right at the hour limit, and I figured I'd give people the option to leave. But we're ahead of schedule.
That's too nice of you.
So a few years ago, I wrote a blog post saying friends don't let friends put JSON in their data links. And the reason for this is JSON is a very limited data serialization format. Sorry, brain not working. It has essentially 3 data types: strings, floating point numbers, and Boolean. And okay, you have arrays and nested objects, but there's really not enough information to really describe your data. And what that means is that every query that goes against the JSON has to know all the rules. So let's take timestamps. That's kind of my favorite example. If you're lucky, if you're really lucky, your timestamp is an ISO 8601, I think is the standard. Timestamp with milliseconds, not microseconds, and a time zone. If you're unlucky, you might have microseconds, which a lot of parsers decide to reject. Or you might not have a time zone and have to know that this is actually local time where the program was running. Or you might have milliseconds since the Unix epoch. And every query has to know what it's dealing with. And oh yeah, timestamps especially, people change. So your data up through yesterday had a particular timestamp format. Today it's got a completely different one. All your queries are breaking. So I much prefer the idea of, sure, you get JSON. That's fine. A lot of things deliver JSON. At the front end, you know what that JSON actually contains. You know how to transform it. So transform it and put something better in your data lake. And Parquet is probably the most reasonable choice. It's columnar, so it's very performant. It's got a schema. You probably heard me say all of this 3 months ago when I did a talk on how to optimize data lakes. So again, developer, I want to keep making things perfect. Why do we want to do that? Should we stop at this point? And there are a couple of reasons. First off, CloudTrail data is really complex. Okay, like I said, it's the access log for AWS, and it contains all the request parameters and all of the response elements, except for the ones that it masks out because, well, you don't want to have logs containing secrets. That changes all the time. AWS does a release of its SDK approximately every day and a half. And that release means that there's something that's changed, a new API call. If you're going to try and represent that in your transformation, you have got a full-time job. Your boss probably won't want to keep paying you for that full-time job. Plus, there's so many different combinations that if you try and accurately represent it, it's going to have this Parquet file with tens of thousands of columns. Actually, I can be a little bit more exact, with approximately 7,000 columns based on the CloudTrail data that we have going into an Elasticsearch cluster. Plus, now, you're going to know the data anyways. CloudTrail, to get beyond the common fields, you have to know what the data is. You're not going to be joining CloudTrail data to marketing data, right? You're very specific why you're going to use this. And quite frankly, a few thousand files in JSON is pretty damn performant. And finally, practically, a day's worth of data comes out to about 6 megabytes compressed, and that's too small for Parquet. In fact, if you wrote a day's worth of data as Parquet, it goes to about 8 megabytes. So those are the reasons to stop, but this is a talk and a demo, and we're not going to stop. So what I'm going to introduce here is a second aggregation step. So our first step took took individual files and aggregated them by day. The second step is going to take those daily files and aggregate by month. And why not do this in one big jump? Well, whoops. Takes 4 minutes. This is one case where performance is an issue. It takes 4 minutes a day. Lambda can run for up to 15 minutes. You'd only be able to process 4 days worth of data, if that. So we're going to have a second step. Now that gives you a question. Should you be deleting the data, right? You process a day's worth of data. Do we just want to get rid of it? Have these steps closely tied together? And I'm going to say idempotency says no, right? Your second step may fail. If you delete the data as part of the second step, now you can't rerun it without going back to the beginning. So yeah, there may be no reason to keep the data, or there may be a reason. It may be that you have lineage requirements for your data lake that says we need the source, we need any intermediate versions, and we need the thing we're actually using. So decision largely based on your company. But if you do decide to get rid of the intermediate step, do it externally to the Lambda. Have a lifecycle rule on S3 that deletes stuff after a couple months. That way you can always go back and rerun. And then the last thing about the second aggregation step is all those nested fields, the things that are specific to EC2 or Secrets Manager or whatever. We're going to just punt on those, and instead of trying to dig into them, we're just going to turn them back into stringified JSON, save it as a string. And now your queries, which have to know what they're looking at anyways, have to parse that. So you look and you say, okay, I'm going to select to run instances. That's easy. That's a top level field. And then I'm going to look for the instance ID that comes back and the user, and you parse the data to actually dig into that. Not a big thing. Although to be honest, CloudTrail is only an example. I think it's much better to dump your CloudTrail into Elasticsearch. So how do we do this? Well, Python's the language of data engineering, right? So PyArrow, which is a wrapper around the native Arrow library. And Arrow, I haven't dug into terribly much. It's manipulating tables worth of data. The only thing I've used it for is data conversion because it can basically read and write any format that you want, and it can do it quite well. Now you might think, well, why not Java? Parquet came from the Hadoop ecosystem, which is in Java. I used to be a Java programmer. The Parquet library for Java is everything bad about the Apache ecosystem. It's been rewritten, partially rewritten, things are deprecated, there's no documentation. Years ago, I actually wrote a program to generate Parquet in Java from a database. The only thing I found that helped me understand how to do that was a blog post that said, okay, first we're going to write an Avro file, and then we're going to use this utility to transform the Avro file into a Parquet file. So PyArrow is the way to go, I think. Oh yeah, the Java Parquet file also comes along with hundreds of dependencies, including things like the Hadoop client, the command line processor for Hadoop. It's so intertwined, they can't pull things apart. As I said earlier, designed for bulk activities. So what we have to do is we have to stage our data as Python objects, and then it provides you one step, a list of Python dicts, write it out as a Parquet file. With some code. First off, Parquet needs a schema. Our schema is pretty simple. I'm taking essentially all of the top level CloudFormation fields, and they're mostly strings, so it's all pretty simple. One thing that I'm doing that I wouldn't do if this was actually production code is I'm leaving the fields camel case. Camel case like that. Unfortunately, when you're dealing with that with Athena, everything turns into lowercase. So if I was really writing this, and I should update this to show that, I would use fields that have underscores, snake case names. And that's no problem because I need a transformation function anyways. So we have the source CloudTrail record, and we're just, for the most part, retrieving individual fields out of it. So I could do event underscore ID there. In fact, maybe by the time you see this presentation, that will be updated like that. The only tricky thing is that I am parsing the timestamps so I can get real timestamps in my Parquet files. Fortunately, the format for CloudTrail is very amenable to the from ISO format. It's ISO with milliseconds with Zulu time zone. And then this is the punting here. All of these things contain nested resources. So I go through, and if it's in the source, I dump it into a string and dump that into the transform record. And then writing is just this. That's it. You have a list of Python dictionaries. You say, turn that into a PyArrow table, and then write the PyArrow table. Done. Any questions?
Where are you going to get this PyArrow table?
This is part of the transformation Lambda. So it goes through and aggregates records just like the previous version, transforms them according to the schema, and then at the very end, actually, whenever it hits a configured number of rows, it'll write the table.
Is this what Data Wrangler is doing under Hadoop?
I'm not familiar with Data Wrangler.
So Data Wrangler
I've heard the name.
is a wrapper that you get from AWS, and it will write Parquet to S3. It's integrated with Glue, so it'll write the Glue catalog entries at the same time, which is convenient. But under the hood, it's PyArrow.
It is.
And so I assume that this is really what it's doing.
Probably.
It's wrapped.
Yes, probably
Yeah.
very, very similar. That surprised me. I would have expected Glue, I thought, was all Java, except for the PySpark version part of Glue, which is a great thing.
It's sending API calls to
Yeah.
Glue when it writes the file and with the information necessary to update the Glue database.
Okay.
Right. So what it allows you to do if you're using Glue is do the write without having to have a subsequent Glue crawl to pick that up and
To
get
pick
it
that
in
up.
the
Oh, that's a nice feature.
Yeah.
I hate Glue, but it's a nice feature. Sorry, I wear my,
There are parts included that are real shit. And there are parts that are actually useful, right? And the catalog is useful.
it's great.
When you have millions of files in
Yes.
Parquet, right?
And the crawler is great.
And
Okay, great being relative to maintaining it all by hand.
yes,
Okay.
absolutely.
So that's the code. That's all the code. There's a little bit here of aggregating records, which I didn't show you. It's like another half dozen lines of code. But really, again, very simple. Okay, well, there's a big problem, which is that PyArrow is big. A Lambda deployment bundle is a maximum of 50 megabytes compressed. PyArrow and NumPy, which it uses, is over that. 23 plus 39 is 62, I guess. My math still works. So the approach you have to use is create layers and upload the layers separately. And layers are a nice feature of Lambda if you don't use them. You can put your dependencies in a layer and you don't need to include those dependencies in your deployment bundle. For this, we need 2 layers because individually they fit in that 50 megabyte limit. Together they don't. And fortunately, there's really not a whole lot to it. When you do a pip install PyArrow, it basically creates 2 downloads, PyArrow and NumPy, and those are the only 2 dependencies. If you're using layers with a Python Lambda, everything has to live under the Python directory. So I use the -T for target into Python, and then all you have to do is zip them up. Nice and easy. You can fit this into a build script. But there's a bigger problem. There always is. PyArrow is specific. It's a binary library. And binary libraries are usually specific to the Python version and definitely specific to the architecture. So if you have a 312, a Lambda running 312, you can't run a 311 version of PyArrow. If you have a 312 version of PyArrow that's for the ARM architecture, you can't run that on an x86 Lambda. If you get it wrong, you're told a somewhat cryptic no module, and you have to look and say, no, I was expecting PyArrow, not pyarrow.lib. PsychoPG runs into this also. It's a reason why I prefer the PG 8000 library to talk to Postgres. Okay, there's some easy solutions here, sort of. Solution number 1 is that you use, AWS provides Docker images for each active supported version of Lambda. So you can, on your laptop, run the AWS Lambda Python 3.11. You have to tell it to run bash instead of, by default, it runs Python. And you have to bind mount your temp directory into an arbitrary directory on it. Then you can just go through and do that pip install and the zips. This is not very deployment pipeline friendly. So this is where I would say use a Lambda container image, which is an actual Docker image that runs in the Lambda execution environment. And there's some rules. You basically take a Lambda handler, just like you would deploy. It has the surrounding piping to make that work. And Lambda container images do have a lot of issues. One of the biggest issues is that if you thought cold starts were bad with a regular Lambda, you're talking a long time for a Lambda container image. But for things like this, it's a really easy build process to say, okay, from the AWS Lambda Python, copy my handler into this directory. Actually, sorry, wrong order. Pip install PyArrow. You always want to do things like pip install, things that don't change in a Docker file before things that change. Copy my my Lambda, done. Upload it to ECR. So I think I could go with more slides about this, but I think we're done. All right, well, I guess thank you all for coming.